Here are the solutions for Chapter 7 homework from the 8th edition of our textbook. Question 3 says, is it possible for a baseball to have as large a momentum as a much more massive bowling ball? So the bowling ball here is much bigger, it has much more mass, but we know that momentum equals mass times velocity. So while the mass is much bigger, the baseball can be thrown much faster. So it is possible to have a small mass but a big velocity and end up with equal momenta for these two. So the answer is yes, it is possible. Question 7. Is there an advantage to following through when hitting a baseball with a bat, thereby maintaining a longer contact between the bat and the ball? Explain. So ultimately what we're trying to do is change the momentum. And we know that change of momentum equals impulse, which is equal to force multiplied by time in contact, the time that the force is acting. So if the time increases that the force is applied, then we will have a larger increase in momentum, or change in momentum, a larger change in momentum. And a larger change in momentum means that it's going to leave the bat at a bigger velocity, which is good. That's what we want. So yes, there is an advantage to increasing the time, to following through. All right, I don't know if my drawing is very good on this one, but it says, what is the advantage of an airbag in reducing injuries during collisions? Explain using impulse and momentum ideas. Okay, so we see our character here is driving along, very happy, holding onto the steering wheel, gets in an accident. The top arrow right here says that there's no airbag. You hit the steering wheel and you come to a stop. That stop happens very quickly. So there's a large change in momentum, a big delta P, in a short amount of time, which means the force is going to be really big. And that's bad. That's why we have a frown. Now, with the airbag, arrow number 2, going down to the bottom, we have still a big change in momentum, but the time is increased. A bigger time means that the force is going to be smaller. Now, there's still a lot of force involved, but the force is smaller because the time is increased. So the advantage of an airbag is that it increases the time for the change in momentum, which decreases the force. Question 20. In question 20 we have two skaters. They're initially at rest, so V for each of them equals 0. V1 and V2 equals 0, which means that the momentum is 0. The total momentum for the system is 0. If the total momentum for the system before equals 0, that means the total momentum for the system after has to equal 0, because there are no outside forces, which means the momentum of skater number 1 in the negative direction has to equal the momentum of skater number 2 in the positive direction. So the question asks, what is the total momentum of the system after they push off? Even though they both individually have momentum, the total momentum after equals 0 kilogram meters per second. In question 28 we have a railroad car that is initially moving right here, and it collides with a second railroad car, and they couple together and move as one unit after the collision. So it's an inelastic collision. They hit and stick together, and the question asks what will happen to the velocity between the initial velocity of the cart beforehand and the final velocity of both carts moving together afterwards. Now, the total momentum beforehand, so momentum here is going to equal the momentum there, because momentum is conserved in any collision, including inelastic collisions like this one. So if the total momentum stays the same, the total momentum beforehand is going to equal the mass of this car times its velocity, P equals m1 times v. But in the circumstance afterwards, we have m1 and m2, so the total mass has increased, which means that this velocity will decrease, so v after is less. The mass is increased afterwards, so the velocity afterwards is going to decrease. All right, exercise number 3. In exercise number 3, we have a bowling ball that has a mass of 6 kilograms and a velocity of 1.5 meters per second. We have a baseball with a mass of 0.12 kilograms and a velocity of 40 meters per second. So we have a big mass in the bowling ball, but a small velocity. And with the baseball, we have a small mass and a big velocity, and we want to know which one has the bigger momentum. So we have to calculate the momentum for each. For the bowling ball, P equals m times v. So it's 6 kilograms times 1.5 meters per second, giving us a momentum of 9 kilogram meters per second. For the baseball, same thing. We have a mass of 1.2 kilograms and a velocity of 40 meters per second, giving us a momentum of 4.8 kilogram meters per second. So the bowling ball has a greater momentum. Exercise 6. A ball experiences a change in momentum of 32 kilogram meter per second. What is the impulse acting on the ball? Well, that's for part A. Impulse acting on the ball. Impulse is change in momentum. And the change in momentum is 32 kilogram meters per second. That's given in the problem. Part B. If the time of interaction, time, is equal to 0.25 seconds, what is the average force, the magnitude of the average force acting? Well, we know change in momentum is going to equal force multiplied by time. So therefore, force is going to equal change in momentum divided by time, or 32 divided by 0.25, which gives us 128 newtons of force. My artistic skills leave a little bit to be desired in this, but exercise 10, we have 2 football players. We have the fullback, number 44. He has a mass of 105 kilograms and a velocity of 3 meters per second heading towards the north. You can see my little compass on the upper right here. Then a defensive back is coming in to make a tackle. Number 26 is coming in at 80 kilograms, so less mass, but bigger velocity, running at 5.5 meters per second south. They collide, and when you make a tackle, you hold on so they stick together. It's an inelastic collision. And we want to know, for A, what is the initial momentum of each player? So P equals m times v, 105 kilograms multiplied by 3 meters per second gives us 315 kilogram meters per second north, and player 2 is going to be 80 kilograms times 5.5 meters per second gives us 440 kilograms meters per second south. I could also, instead of saying north and south, I could have said positive and negative. I could have said north is positive and south is negative. So I could have had an answer of 315 kilogram meters per second and negative 440 kilogram meters per second. Either way is fine. Part B. Part B asks us, what is the total momentum of the system before? The total momentum of the system, remember, momentum is a vector quantity. So it's going to be the momentum in the positive direction minus the momentum in the negative direction. So it's going to be 315 kilogram meters per second minus 440 kilogram meters per second, which is going to equal negative 125 kilogram meters per second. All right. Part C asks what direction, if we ignore the external forces and they stick together as one mass, what direction will they be traveling immediately after they collide? Since the momentum initially is in the negative direction before the collision, the total momentum afterwards will also be in the negative direction, so they will be traveling south. Another way to look at it, the momentum of the defensive back is greater initially, which means the total momentum is in the direction of the defensive back. So the momentum beforehand is in the direction of the defensive back. That means the total momentum afterwards is going to be in the direction of the defensive back, meaning it's going to be south. Exercise 12. A rifle with a mass of 9 kilograms fires a bullet with a mass of 6 grams, which is 0.006 kilograms. Immediately after it's fired, the bullet has a velocity of 750 meters per second. We're asked A, what is the momentum of the bullet after it's fired? So P equals M times V. We know M is 0.006 and V is 750. So 0.006 kilograms multiplied by 750 meters per second gives us a momentum of 4.5 kilogram meters per second. Part B says if external forces acting on the rifle are ignored, what is the recoil velocity? So it initially has a total momentum of 0, which means afterwards the total momentum is also going to be 0, which means the momentum of the bullet has to equal the momentum of the gun. So momentum of the bullet we found to be 4.5. That means the momentum of the gun is going to be 4.5, and P equals M times V. We know M, and we know the momentum is just in the opposite direction. It's 4.5 kilogram meters per second equals the mass of the gun, 0.9, times V of the gun. We end up with the velocity of the gun of 5 meters per second. Last but not least, we have a pitcher throwing a fastball at 40 meters per second. It's struck by a baseball bat, so the ball gets hit and heads back at 60 meters per second. But that is in the negative direction. It's in the opposite direction, heading back towards the pitcher. The time that the bat and ball are in contact is 0.04 seconds. And we also know the mass of the baseball is 120 grams or 0.12 kilograms. All right, A. What is the change in momentum of the ball during the process? So it has an initial momentum, change in momentum, delta P, is going to equal final momentum minus initial momentum. Final momentum is going to be negative 60 meters per second multiplied by its mass, which is 0.12 kilograms, minus its initial. The mass doesn't change, 0.12 kilograms, times its initial velocity, which was positive 40 meters per second. So we end up, after doing that, with a change in momentum of negative 12 kilogram meters per second. B. Is the change in momentum greater than the final momentum? When you do your calculation here, the final momentum is this one, you're going to find that it is, in fact, less than the total change in momentum. So the answer is yes, but it asks you to explain. Now, how is that possible? How can the change be bigger than one of the components? Well, it's changing direction, which means that the total momentum change includes going from its initial momentum in the positive direction coming to a stop and then gaining momentum in the negative direction, which effectively causes a larger increase in change in momentum. So the answer to B is yes. Part C, what is the magnitude of the impulse required? Remember that impulse equals change in momentum. And we just figured that out, so impulse is negative 12 kilogram meters per second. And lastly, what is the force required? And we recall from previous problems that force is delta P divided by T. We know delta P is negative 12 kilogram meters per second, and T was given in the problem as 0.04 seconds, giving us a force required of 300 newtons in the negative direction. That's all. If you have any questions, please feel free to send me an email. Have a great day.